Hello, it's Dr. Harris, and we're back with the second video from Chapter 8 in Math 111, our statistics course, and we're going to continue looking at a couple of topics within the subject of linear regression. In the previous video, we looked at correlation, we looked at looking at scatter plots to determine when we had linear association. When we did have that, found correlation, we found an approximation to the regression line. Then we used an RStudio command, LMGC, to find the actual equation of the regression line. And then we saw that we could use regression to do prediction, and we also could use it to find residuals. And we want to follow up on these topics a little bit more in this video. So we're going to talk about residual plots and prediction intervals. So we want to remember that a residual was the difference between an observed response and the response predicted by the regression equation. And so it's the actual response minus the predicted response. And one way, if we can go back and judge whether or not regression was really the right tool to use. We thought it looked linear, we went ahead and regression, but a residual plot is one way we can actually tell whether we were right to think that maybe that regression was a good tool to analyze our data set. So let's see what a residual plot is. So just a quick reminder, this is an example that we looked at in the previous slideshow. This is our scatter plot of high temperature at a rails to trails park, along with the number of participants on that rails to trails during a given day, measured over 90 different days in one season, 1 year. And we saw that there was a general upward trend as the temperature went up. Number of participants tended to go up, and we found the equation of the regression line using an approximation method and LMGC in our previous video slideshow. So just a reminder of some of the output. When we ran LMGC, our correlation was 0.5826. The regression equation was that volume of traffic will be negative 17.08 plus 5.702 times the high temperature. And so here's what we can do once we've got the regression equation, what we can do to find the residuals. And so we're going to require a little bit of different setup than what we've seen before in our RStudio commands. We're going to store our residuals in a variable called resids_a. And this command will allow us to compute all of the residuals all at once. And so the construction that we need, though, is taking the data set name, $ variable name. And so out here, this is our response variable, the volume, rail trail $ volume. And we're going to subtract from that the predicted response. And so here's our intercept for our regression equation plus the slope times the explanatory variable, which we write as rail trail $ high temp. And so this is the observed response. This is the predicted response. And so we're finding the residuals, and doing this for putting just the variable names in here computes it for all values in our data set all at once. That's pretty cool. I'm not going to show you the outcome of resids_a, but we are going to do a scatter plot. And so we'll have resids_a as our response, and we'll use the original explanatory variable, high temp, here as well. And so this is the residual plot. There is a relationship between the scatter plot, original scatter plot, and the residual plot. In some sense, it's just a little bit rotated, where the regression line is now made more horizontal, or made horizontal. But I want to focus on residuals equals 0, this horizontal line here right across. And so if we go to the next slide, the value 0 on the vertical axis will always be there. I remind you that a residual 0 would mean that the predicted and actual response matched exactly. And so the question then is, if I go back here and look at this, what do I want to see in a residual plot in terms of scatter about residuals equal 0? And the answer is I want to see nothing. I want to see no pattern. I want to see just a cloud of points. And to a certain extent, I've got that here. There doesn't seem to be any particular pattern, but I do want to make one observation here. And I say, note the cluster of negative residuals on the right end of the plot. And so, sorry, wrong direction. So over here on the right end, I've got a bunch of negative residuals. They fall below the line resids equals 0. And so what we're seeing is that when the temperature is really warm, I have negative residuals, or seem to have only negative residuals. And so what that means is that maybe I've got a bit of a pattern here that I really don't want to see, and that is when the temperature is really hot, that tends to suppress traffic, and we get less than what the regression equation would predict for us to have. But other than that, I'm not seeing a whole lot of pattern here, and so that makes me feel at least moderately comfortable in saying that linear regression was a reasonable choice here. Might have been better on a narrower range of temperatures, but that would not reflect the data that we actually collected. So we don't want to do that. But just a reminder that in the residual plot, we're trying to see no pattern. As an example of a pattern, we see here definitely some sort of pattern to the residuals. It's following some sort of upward trend line or maybe slight parabolic thing here. And so we definitely would not want to use linear regression in a case like this where we see some non-randomness to our residual plot. And so the question becomes then, well, maybe we should ask, well, what was this data set? Where were we seeing this sort of non-randomness to the residuals? And it's this scatter plot involving temperature, outside monthly average temperature, and amount of paid on a gas bill that we encountered in the previous slideshow, where we saw the curved element at the higher temperatures here. So now I'm going to invite you to do a couple of residual plots. We've looked at two other cases, two other examples in the previous slideshow, one involving larvae versus stumps in the stumps data set. Let's come up with a command that will store the residuals for that. We've got the regression equation for that from the last slideshow. So we can store that in resids B, look at the residual plot there. And then also I asked you to look at systolic versus weight from NHANES 18. And so you should have a regression equation for that data set as well. And so you can come up with a command and store them in resid C for the residuals for that case, and generate this residual plot and make a comment. We'll go over these in class and do them in class, but I want you to try them ahead of time as well. So that's residual plots. Now let's talk about prediction intervals. And I pointed out some output to LMGC that we didn't address in the previous slideshow, and that was the output for residual standard error. We've seen that in this course that standard error is somehow a measure of how spread out data is, and the primary thing that we've seen standard error used for in the past is to construct confidence intervals. And so what I want to do here now is talk about a different type of interval called a prediction interval. So let's contrast that with a confidence interval for just a minute. A confidence interval was a range of values on which we thought it was reasonable to believe that a parameter lived. A prediction interval instead is going to be a range of values on which we believe an individual response is likely to live. So, for example, instead of trying to come up with an interval for the mean amount of traffic for a given temperature, we're trying to come up with a range of values that we think an individual day with that specific temperature would have, the amount of traffic that an individual day with that specific temperature would have. So again, confidence interval, range of values that we think is reasonable for a parameter such as a mean. Prediction interval, a range of values that we think an individual response is reasonable to live on. The form of a prediction interval is going to be very similar to that of a confidence interval. We're going to have a statistic, but our statistics this time is not going to be a sample statistic, but it's going to be the prediction, the value predicted for a particular explanatory value. So it's a particular value of y hat. And that's going to be plus or minus a multiplier t star times the standard error for prediction. So instead of a standard error for the mean, we're going to have a standard error for prediction. That's going to be our residual standard error here. And so t star is going to be found just like before. We have our number of degrees of freedom is going to be one less than the sample size. And we will use the two-tail heading to get the right column in the t-table. So let's do a prediction interval using our Rails to Trails data. In the last slideshow, we found the predicted value for using the regression equation for a day on which the temperature is 70 degrees. And so now what I want to do is I want to use that information to find the 95% prediction interval for volume on a single day in which the temperature is 70. Rather than the mean response, we're going to find an interval for the response that we might get on a single day. So we're going to use the regression equation here. We're going to use the standard error for that. So the important thing here is to use the standard error of 104.19, rounded to 2 decimal places. So just a reminder, in the previous slideshow, when the temperature was 70 degrees, we predicted that there would be about 382 people. That would be the predicted volume for traffic on an average. And so we're going to use that figure to get our prediction interval. So that's where this 382 came from, the previous slideshow. There are 90 data values in Rail Trail. And so let's remind ourselves that means that there are 89 degrees of freedom. So for a 95% confident prediction interval, we're going to come here, we'll round down to 80 degrees of freedom. We're going to use the two-tail 0.05 for a 95% prediction interval. And so our value is going to be 1.99 for t star. And so we get 382.07 minus t star times the standard error. That turns out to be 174 3/4 almost. 182.07 plus 1.99 times the standard error gives me almost 589.5. And so we're 95% confident that on a day with a high temperature of 70 degrees, on any day, the number of people visiting this Rails to Trails will be between 175 and 589. So again, this is predicting a single response for a day with that temperature, not a mean response. And so it turns out that standard error for predictions is much wider than the standard error for a parameter. And so we would expect a much wider range of possible individual responses than we would for a mean response. So we should expect a prediction interval to be much wider than a confidence interval. Now I'm going to let you try an example for a prediction interval, do a prediction interval for a plot with 4 stumps. Previous slideshow, I asked you to come up with the predicted response for a plot with 4 stumps. Now I want you to come up with a prediction interval, 95% prediction interval for a response of a single plot that has 4 stumps. And we will talk about that when we get into class.